Welcome back here, and as we continue our discussion of the integration process, and we're in section 5.4 titled Indefinite Integrals and Net Change. Here there's nothing indefinite about this integral here. We've got an a and a b. We're integrating this function f prime of x dx, and notice, well, what is the antiderivative of the derivative? Well, you get back to the original function. Okay, and this is the change. So this is measuring the change in the function cap f from b to a. Units on this thing, let's look at something. If I would integrate something like r of t dt, let's look at units of this. This might be gallons per minute. I just want to remind you what you're doing. And this could be minutes. And I would, well, I guess maybe I should make that little r. And we're going to go from, I don't know, 3 to 5. This is just going to be big cap R of 5 minus big cap R of 3, where this is the antiderivative. And what we're really adding up here is gallons. So this could be something where we'd measure, this might be the number of gallons in the tank at time equal to 5, and this at 5 minutes, and this could be subtracting off the amount of gallons in the tank at 3 minutes. So this would be the net change. So this would be the change in volume. From what? From t equal to 3 until time equal to 5 minutes. Okay, so when we integrate a rate, we come back with the original function. We can add that up. And let's look at some examples from particle motion then, which will make this even clearer, I think. But there's all kinds of word problems, interesting word problems surrounding this concept. They're usually pretty easy to tease out if you, again, you look at the units. Look at the units in the problem. Okay. Well, let's see here. We don't want that. Let's go to, look here. Here's where we're going to, say we'd integrate here from 2 to 8, and we're going to integrate v prime of t dt. Now, what would the velocity, the v is now the velocity. So what would be the derivative of velocity with respect to time? Well, first of all, the units here would be meters per second. Let's say meters per second squared times, this would be seconds. So really I'm adding up meters per second. Okay? Meters per second. If this is seconds, and these are seconds, meters per second. Well, what is the antiderivative of the derivative? It's just the velocity, right? It's the velocity of t evaluated at 8 and 2 is just going to be the velocity at 8 minus the velocity at 2. This is going to be the change, the net change in velocity from time equal 2 seconds to time equal 8 seconds. Okay? Now, what is, again, what's another name for v prime of t? Well, that's just the integral. If we integrate the acceleration, that's equal to the same thing, right? And we'd recognize that. Okay, what if we did, like, I don't know, from -5 to 6 of s prime of t? S prime of t. Maybe we should start at 0. Yeah. Let's think about that again. Maybe not. Let's start at, we'll change colors 1. Remember, we are, okay, I changed colors here. Now notice when I do this, just a little reminder here. Let's stay with green for a while. This is really t equal 1. Notice I'm integrating on time. T equals 6. Well, what's the antiderivative of the derivative? That's just going to be s of t, right? That's the antiderivative. The derivative of s of t takes me back here. That's correct. So now I put in 6, I put in 1. Sorry, that's a 1, not an 11. So this is going to be s of 6 minus s of 1. Well, what is s of 6? This is the position at t equals 6. This is the position of the particle at t equal to 1. So what is this whole thing? It's the change in position. Change in position over t equal to 1 to t equal to 6. Okay, change in position. It could be 0. It could be negative. You know, this is not the distance travel. We're going to get to that soon. Remember, we were interested in that question, distance travel. This is the change in position. So let's look at a particular problem here next. Okay, we're back with a particular example now for particle motion. We've got our velocity curve here. Got our time curve, and remember all the good things here. When did the particle turn around? Well, it turned around at t equal to 1 and t equal to 5. And say I was interested in, let's talk about, well, we could first of all talk about the change in displacement. Say I wanted to know what was the change in position from s equal to 0 to s equal to, oh, I don't know, 3. Oops, that's supposed to be 3 right in the middle. That's t equal to 3. Okay, what is my function here? I designed this to have a 0 at 1 and a 0 at 5. So what is it? It's t squared minus 6t plus 5. And what was the first question we wanted to say? What is s of 5? Oh, that's s equal 3, sorry. What's s of 3 minus s of 0? Well, that's just going to be the integral of s prime of t dt from 0 to 3, which is the same thing as the integral from 0 to 3 of the velocity of t. What's that going to be? Well, we'll put in the velocity of t. It's just t squared minus 6t plus 5. Okay. We integrate that guy, and what do we get? We're going to get t cubed over 3 minus 3t squared plus 5t. And we're going to put in the endpoints of 3 and 0. And what are we going to get? 27 over 3 is 9 minus 27. That's going to be 9 times 27 plus 15. And what's that going to be here? It looks like 24. It looks like minus 3. What does that tell me? The particle from time 0 to time 3 has moved 3 units to the left. So at time equal to 3, the particle is sitting 3 units to the left of where it was at time equal to 0. This is a change in position. Now, it's not the distance traveled, right? Not the distance it traveled at all. Remember how we used to calculate distance travel? If we did distance, what we used to do is we would calculate the change in position between the times it turned around. So how we used to do this back in the good old days when we did it the hard way, we'd say, oh, this is equal to, remember, this is straight line motion. It's straight line motion, so we also drew a diagram that kind of looked like this. We said, okay, it started at 0 and it went to time equal to 1. It went from 0 to 1, then it turns around and it goes back to t equal to 5. Yeah. Okay, and we had this, so it goes this way. At t1, turns around at 5, and at 5, it turns around again and goes the other way. So the distance traveled would be s of 1 minus s of 0. Okay, and then we'd take what? S of 3 minus s of 1. And that would have been, well, how are we going to do this in our, with our integrals? Well, we have to make this, what we need to do is calculate this distance here. We're going to do the area under the curve here. And this, maybe we'll call that part 1. Part 1 is going to be, we're going to integrate from 0 to 1, v of t dt. Okay? Plus then part 2. Part 2, we're going to calculate, and we'll color this red. I want this distance here, but I'm going to make that negative that distance, and it's going to be from 1 to 3 v of t dt. So in essence, the distance traveled, I'm going to make I'm going to add up the actual areas here. It's not the integral, I want the area. I want the area. So if I could do this, I guess I got the same antiderivative here. And with my distance traveled, in fact, I almost want to clean this up. I'm going to clean this up and go to a new page. Hold on, I'll pause it and be right. Okay, I did a little cleanup here. You see I've broken this integral now. I'm calculating distance traveled. And so this is the old way. We want to calculate the change in position to the points where we turn around. So I do the integral from 0 to 1. 0 to 1, right? I go to the first point where we turn around, and I calculate, I do the antiderivative, I plug this in, and I get what? 1/3 minus 3 plus 5 minus 0 at the other end. So this looks like it's going to be 2 1/3, or this is going to be 7/3. Notice, what did I just calculate? That's just the position at time equal to 1 minus the position at time equal to 0. So up here on this one, I must have got all the way out to 7/3. I moved 7/3 distance from 0 to 1. Now the other way, I'll calculate this one. This is going to be t cubed over 3 minus 3t squared plus 5t. Now I've got what? Top integral of 3, the lower integral of 1. When I put in 3 here, I get 9 minus 27 plus 15. This is s of 3, right? Minus s of 1. Well, s of 1 looks like it's going to be, it's going to be 1/3 minus 3 plus 5, or this is going to be s of 1, and s of 1 just looks like it's, this is 7/3. That's 7/3 up here. This is 14. That's 15 here. It's 24. This is minus 3. So minus 3 minus 7/3. This is going to be 9/3 minus. This is going to be minus 16/3. Okay, so it moves to the left 16/3. It goes this way 16/3. Notice, though, I've got a negative of a negative. Okay, so my total distance traveled is going to be what? It's going to be 7/3 minus a minus 7/3 here. I got a little bit sloppy. I'm sorry. It's going to be 23/3. It's going to be my distance traveled. Now, a cleaner way to talk about this, when you want to find distance traveled, is the following. You're going to integrate the absolute value of velocity. This is how you calculate distance traveled from 0. This is distance. This is the distance integral right here. You integrate what? We had another name for this. What did we used to call this? We integrate speed. So this makes perfect sense. If we integrate speed times time, we're going to get distance traveled in first 3 seconds in this case, right? So again, how would you, if you wanted to redraw this curve and make it speed, you would just redraw a function here. The function would now look like this. It would come down. Instead of going below, it would come up like this and then over. And so what did we do? We went up to t equal to 3. T equal to 3, and we calculated the area under this curve. What is this curve now? This is the speed curve. Okay, so if we integrate speed over time, we get distance. You'll see that a lot. Know that well. That question gets asked a tremendous amount. Okay, see you soon. Bye-bye.